Hello, today we are going to start day 1 of chords. This is section 10.3 in your Pearson. Now I am going to be going kind of fast. I have some of these theorems already written down, so feel free as you need to pause the video so that you can stay caught up and make sure that you're getting all the notes that you need. First, we're going to define what a chord is. So a chord is a segment whose endpoints are on the circle. So as I draw my circle, I could have a chord here, endpoints on the circle. I could have a chord that goes from here to here. As long as those two endpoints are on a circle, those are chords. So throughout, we're going to do a couple proofs. No, you won't ever have to do these on a test, but I think that it is good to be able to see where certain things come from, and you should see some familiarities with what we did last semester. So first we want to know, why is RS congruent to UT? So why is this chord congruent to this chord? Well, the first thing that you may notice is that we have our vertical angles already marked on our picture. So angle SQR is congruent to angle TQU by being vertical angles. So that vertical angles theorem. Another thing that we know about circles is that all their radii are congruent. So RQ, SQ, QT, and UQ, those are all going to be congruent. So QS is congruent to QR, which is congruent to QT, which is congruent to QU, because they are all radii of that circle. Now I can see that triangle SQR is congruent to triangle TQU by SAS congruence theorem. So a throwback to semester 1. Therefore, I can now finally say that RS is congruent to UT by, you guessed it, CPCTC, one of our favorite theorems. So therefore, you know that this chord will be congruent to this chord, assuming they have the same central angle. So like I said, I already have this written down, so pause it if you need, but you can see that we have a theorem and its converse. So if MN, this chord, is congruent to chord PQ, then we know their central angles are going to be congruent as well. The converse below is also true. If I know those central angles are congruent, then their chords are going to be congruent as well. So that is our first theorem, relating our central angles to those chords. Now I want to know why AB is congruent to CD. So I took this and I actually took out the given, but we actually are given in this problem that AB is congruent to CD. And that's kind of important. So just know that this was given in the original problem. I just didn't include it on your notes. So we know that this arc is congruent to that arc. Therefore, we know that the measure of arc AB should be equal to the measure of arc CD, just going between congruence and equality. Therefore, I am going to add in kind of these dotted lines here. So we learned before that central angles have the same measure as arcs. So I can say that measure of angle APB is going to equal the measure of angle DPC, and that is because my central angle is equal to my intercepted arc, and we learned that in 10.1. Therefore, I can say that AB is congruent to CD by theorem 10.3 above. So I have the same central angle, so therefore the chords are the same. That leads us to our second theorem. Given the same arc, we can say we have congruent segments. So theorem 10.4 in the converse, if I know that my arcs are the same, then I know these chords are also going to be the same. And vice versa. If my chords are the same, then my arcs are also the same. The third thing that I'm going to prove is, why is AB congruent to CD? So now I'm looking, why will this distance be the same as this distance? Now this proof we're going to take out a little bit, so stay with me. But first we're going to look, and I'm going to say that triangle APE is congruent to triangle BPE, which is congruent to triangle CPF, which is congruent to triangle DPF. So I'm looking at all of these little triangles. Here's DPF, CPF, APE, and BPE. All four of those little triangles are going to be congruent. We're using HL for this, and essentially we know that our radii are going to be the same, and we know the chords are equidistant from the center. And that was given to us in the problem. That, again, I don't have written here, but that was given to us. So therefore, we have our radii, which are our hypotenuses here. And we also know that these chords are equidistant from the center. So PF is the same as EP. So you can see right there, because we have those right angles, that we can use HL. So those four triangles that you see there are going to be congruent by HL. And now we can look at this second picture down below. So I know that AE is going to be congruent to BE, which is going to be congruent to CF, which is congruent to DF by, once again, our favorite theorem, CP-CTC, or at least my favorite. So I know that this piece here is congruent to this piece here, which is congruent to this piece here, which is congruent to this piece here. Again, CP-CTC, all four of those pieces are corresponding in the triangles above, so they'll be congruent. So now I'm going to do a little bit of addition. So I'm going to take AE plus EB, the two on the bottom here, and I'm going to say that that equals DF plus FC, which is these two. And once again, I'm adding up essentially the same segments. So they will be equal to each other. And if you want, you can really just say that that's going to be substitution. I get AB, that whole chord, is going to equal DC. So therefore, AB is congruent to DC. Now, like I said, that theorem, we'll use it. You're not going to have to prove it again, but you do have that if you have chords that are equidistant from your center, then the chords will be congruent, which this very, very quick and brief proof shows. So we have a theorem that says we can say that's true. So here it says if chords are equidistant from the center, so that means that SE and SF here are congruent because they're the same distance away, then the two chords will be congruent. So you can see my chords AB and DC will be congruent. And the converse is over here on the right in pink. It works the other way. So if AC is congruent to CD, so now I know that the chords are the same, then I know that they're going to be equidistant from the center. So therefore, SF and SE are going to be congruent. So those are most of my theorems. So we're going to look at a couple problems really quickly before we do our final theorem. So here I have this example. They tell me that EF is equal to EG. That's good because I have lines or chords being congruent from my center. And they tell me that CG is 20. So that distance right here is 20. And I want to find AB, this whole distance. Well, I know that because these are marked as congruent, this piece will also be 20. Therefore, CD is equal to 20 plus 20, which is 40. So this whole chord is going to be 40. Because AB and CD are equidistant from the center, I know that AB is equal to CD using the theorem we just wrote down. So therefore, AB is also equal to 40. For this problem, in circle P, the measure of arc AB is equal to 43, so that's this arc right here, and AC is equal to DF. So I have this chord is congruent to this chord. I want to find the measure of arc DF. Well, I know that the measure of arc AB is going to equal the measure of arc BC, which is going to equal the measure of arc DE, which is going to equal the measure of arc EF. So essentially, all of these arcs are going to be congruent. So therefore, they all equal 43 degrees. So if I want to find the measure of DF, this whole arc, the measure of arc DF is just going to equal 43 plus 43 which is equal to 86. So the measure of DF is equal to 86. So we were able to say that because those chords were congruent, so therefore each of those pieces were going to be congruent. The final example is a little bit more challenging, so we're going to break apart the problem a little bit. It says the corporate headquarters, an executive wants to place a company logo that is 6 feet in diameter with the sides of the H 5 feet tall on the front wall. What is the width of X of the crossbar for the H? So essentially, what we're going to look at is I'm going to redraw this. So I have my circle and I have my H. So the sides of this H here are chords, and here's my H. Now, they tell me that I want to find X, this distance. So I'm actually going to look at this little triangle right here. I'm going to make a little right triangle. Now, they tell me that I have a diameter of 6, so my radius is equal to 3. So when I'm looking at this little H here, and I look at this right triangle, I'm going to cut that piece in half, and I know that I have a radius of 3. So this piece right here is 3, because that's the radius of my circle. From the center of my circle at the H here to the side, that's my radius. Then I know that this width in between my H is going to be X. So halfway through that is 0.5x. So that means that this piece right here is 0.5x on the bottom, half of the width of that H. And then finally, they tell me that the H is 5 feet tall. So that means that halfway up my H, it's only 2.5 feet tall. So halfway up here would be 2.5. So that means that this piece right here is 2.5, half of that H height. So essentially what I'm doing is Pythagorean theorem, which we have done a lot of lately with 0.5x, 2.5 here, and my radius of 3 right here. So if I do that Pythagorean theorem, I have 0.5x squared plus 2.5 squared equals 3 squared, because that is across from my right angle, my hypotenuse. Now this algebra does get a little tricky, but when I square both these 0.5, so 0.5 squared is 0.25, but I also have to square the x, so I have x squared, plus 2.5 squared is 6.25, and that's going to equal 3 squared, which is 9. What I'm going to do is I'm going to subtract 6.25, so I get 0.25x squared is equal to 2.75. And then I'm going to take and divide by 0.25. So 2.75 divided by 0.25, I get 11. And the final step is to take the square root. So I get x is equal to 3.32 feet. So that is my value. We'll talk about that in class. So if you have questions, don't worry about it. It is a challenging problem, but it is kind of a nice little application of these things that we've learned so far today. Here's my final theorem, and I'm going to write it out. So if CD is a diameter, AB is perpendicular to CD, then AE is congruent to BE, and the converse works as well. So if, once again, CD is a diameter and AE is congruent to BE, then AB is perpendicular to CD. So we'll talk about this on Monday.